Thank you very much. So I'm lucky person who's going to define stable matching. It's our blocker. Okay. It's okay, there is not.
I will send it.
Yeah. Alright. So that's the focus of the following. I talked about stable marriages and the generalization of this particular stable allocation. And I entitled definitions, I'm going to talk about dynamics. So what happens if you leave the system work on its own way. So the very basic things about stable matching. You're given a set of men. Up there is 4 vertices, that's the women. Down there are these 4 vertices. Some of them usually know each other. The graph does not have to be complete by perfect graph. And every participant ranks all his neighbors in a strict order of preference. Number 1 means first choice edge, the crush. Number 2 means the second choice. 3 is still okay, and whoever is not listed is not acceptable for the person. We are searching for a matching, which is a set of edges that no one is married to more than one person. And we say that this matching is stable if there is no edge blocking it. A blocking edge is an edge which is not in the matching, and both endpoints would benefit from switching from the existing matching to that edge. We know it for more than 50 years that a stable matching always exists in a graph. So these are the very, very basic things. And how to find a stable matching, but I guess most of you also know this one. This is the data chapter algorithm goes the following way. Men propose on their first choice edges, and women who get more than one of those, they only choose the best one. Unmatched men now propose again. Women also, again, accept or reject. And so on. And at the end of this presentation, you get a stable matching. So this was a very basic introduction to stable matching. Now what we do is dynamics of stable matching. So we assume that you have a system where everyone has a fixed preference list, and then we work on that. Now in real life instances, like dating, this is not the truth. So you change your preferences, there are new people coming into the instance and so on. So our question is the following. Given a matching, which is not certainly stable, if you see that there are blocking edges, then the system on its own would take in the blocking edges and throw out some superface edges. So by adding blocking edges all the time, are you going to reach a stable solution or not? This is the big question, which was answered by Ackermann, in many stages it was answered for stable matching instances. So I'm going to start with this sample instance. The matching you start with is the blue edges. Of course, it's not stable. For example, this edge is have boxes. So this is the first blocking edge you can take in. A box because this one would prefer to be matched, and this guy is unmatched, so this edge box to matching. So you take it in and you throw out that edge. This is a myopic change. And then you go on. This is again a blocking edge. And you just go on saturating blocking edges and throwing out vertex edges from the graph. And you can see that we actually can run the cycle. We got back to the matching we started with. So even if it would be intuitive to just add blocking edges, you're not going to reach a stable solution. Not in all cases, not in all paths. So we call this a path to stability. If executing myopic changes leads you to a stable matching. So this example also shows that these uncoordinated processes using myopic changes, they may cycle. On the positive side, we also know that they terminate in probability 1. So actually, people who got considered the example, they actually have to work quite hard to find an example where myopic changes actually run the cycle, because usually you terminate with a stable matching. So this much about stable matching and path is the stable matching. In practice, you usually, there's some more for it. So we also know that there is a best response strategy leading to a stable matching. How do we make best response? So I haven't defined player advantages, of course, on this. So what usually in the literature, you just say that this side, men are active players, they have strategies, and women are the passive players. And a best response step is a blocking edge is the best blocking edge for the man. So you choose a player, a man, and he can saturate any blocking edge, but if you play, which is a better response tab, if you play the best response tab, then he will saturate, he will take in his best blocking edge. And you know that even such changes can run in cycles, but there is a best response path. It provides instances at least a stable matching in all the time. So the idea of this paper, how it works, is first you have an instance, some men are married, some are not. And you first let the married man propose. So you ask one a married man, which one is their best blocking edge. By these operations, some men can get unmarried. Whoever is unmarried stays quiet in the first round. And there is a point where all married men say, I don't have blocking edges anymore. And then you ask the unmarried man to add their best blocking edges. It's not straightforward to see, but this actually terminates in polynomial time. This is the good liturgy. So for the instance we had, this is it. You remember the cycle. So first you have to ask the married man what their best blocking edges are. This is the first married man who has a single blocking edge, and then you add this to the graph. Now you ask the married man what blocking edges they have. They will say this is the end of the first round, we don't have blocking edges anymore. And then you ask the unmarried man, the single guy, what is his best blocking edge, and voila, you reach a stable solution. So even though we could run in a cycle, there is a very short path using best responses to a stable solution. So in practice, stability is very often used in extensions of the stable marriage problem, such as college admission, which is still a bipartite graph, but it's a one-to-many matching. Colleges have several slots for students. And then top scheduling, which has many-to-many matching. You have machines and jobs, and you have to order them to each other according to their preferences. I'm going to talk about this a bit later. Or roommate allocation, which gives you a non-bipartite graph. So the one with tackle is actually a big generalization of the first two ones. So we still talk about bipartite instances, the capacities and quota. Here's the setting. Instead of men and women, you have jobs and machines now. And jobs and machines have quotas. This is what the number in the vertex. So a job wants to be allocated in at most time units of 2. A machine has at most time units of 3 to spend on jobs. So you can partially fill up this quota. You can never go above this quota on either side. And then in addition to this, even edges have capacities. We're not matching instance anymore. There are two sorts of edges in this example. The thin ones, they are of time unit 1, and the thick ones are double edges, they are time unit 2. So the general model does not involve any interpretive constraints. You can have theoretically even a directional input. Of course, it would be programmed the directional input. So these are arbitrary functions, non-negative functions and edges, and then one on the jobs, one on the machines. So this one is a feasible allocation, for example. You fully assign this job to this machine. You assign 1 unit from this job to this machine, filling it up. And then you assign the entire job along this thick unit 2 edge to this single machine, filling it up. And an edge blocks if it's unsaturated, and both endpoints would benefit from adding some more allocation on this edge, which means they either have free quota to allocate, or they have some quota allocated to worse jobs or machines. So experience tells that some people get stuck with this definition. It's not very straightforward. So if you feel like it's a bit complicated, just think about B matchings. It's just complicated matchings.
So you may have, when you say an incomplete job is one which is not fully allocated.
Yes. 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 So this is the stable allocation instance, which is a high generalization of stable marriage, one-to-many and many-to-many matching as well. And we always also know that there is a stable allocation which can be found via modification of the VHFT algorithm, still in polynomial time. So this one is a blocking edge, for example, because the job would like to switch, the machine would like to switch. This one is also because the job has some more quota to allocate, and the machine would like to switch. Okay, so we are interested in dynamic procedures. So you're given a feasible allocation, and you want to saturate blocking edges. Are you going to arrive to a stable allocation? Now the answer is of course not always, because you already have counter example for the matching case. But is there an efficient algorithm like the one we saw at the end of the previous section that always reaches a stable solution? This is the main question of our contribution. So I'm reminding you what was the good strategy for stable matchings. First you ask the married man, and then you ask the unmarried man to improve their positions. Now it cannot just do this because the active side can be partly married. So it has already freed up half of its quota. So how do you decide when to start and who to activate them? And our idea is also a two-phase algorithm, which can be seen in generalization of the two-phase algorithm from the Ackermann paper. And it says that first you freeze the quota. So whatever unit of time you already have allocated at the beginning, you never go above it. You never go over it. You just keep that, and whenever you take a blocking edge, you reduce some allocation on some worse edge, even if you would have lots of free quota. This is what corresponds to the married man principle. So they have a blocking edge, they take it in, but they have to refuse something. We will keep this, and then once we are through this range, and everyone who has some allocated edges, they are through, then we start to allocate the free quota. And we show that this procedure will actually be often converged to a stable matching or a stable allocation. So this one as a sample run of it. So this job who has 2 units of time allocated has a blocking edge, this one. So we take this in and notice that the job has 2 units allocated and 3 units of quota, which means he could just add this edge without deleting anything. But the idea of the first round was to reduce the allocation on the worst edge, because he froze the quota. He cannot go over his current allocation of 2. So this vertex has to keep the matching property, has to reject the edge, but the job still rejects 1 unit of allocations from this, even if the job would have one more unit of quota. And then we just ask again this job whether he has free or a blocking edge. He says again yes. And then you take in this edge with 1 unit of time. And now all the jobs will say, I don't have any more blocking edges that are under my, or that are better than my worst allocated edge. So you will free the quota, and you will fill up the quota at jobs. So this will be taken in with 1, because the job only has 1 unit of time free to allocate. And then this is also a blocking edge. Take it in. 1 more blocking edge. You take it in. And this is it. And then you reach the stable allocation. So very shortly about the proof we have. How does it work out with the main idea? Well, we had an underlying algorithm for much simpler instances. And then we just derived it to one-to-many, many-to-many, and then to rational allocations. And then we actually got over this sort of artificial constraint of being rational, because, well, I know the computer scientists will say, yeah, who cares about irrational input, but we actually have an algorithm that also works on irrational input, which would be quite nice. So how does the proof work? Of course, it has to prove correctness and then polynomial combination of this algorithm. The correctness uses a hamper graph. There you have proposal and possibly proposal and refusal edges. And you try to put down in alternating blocks, in cyclical blocks. And the very interesting part here is that best response is worse than better response. So we actually have instances where playing best response strategy also leads to a stable allocation, but it might take exponential time. So there are instances where definitely there is a single path to stability if you use best response, it is exponentially large or long. On the other hand, if you say a better response with freezing the quota and reducing the quota of vertices, even if the job would have some free quota, then you actually reach a solution in polynomial time, which is, I think, quite surprising. So best is not the best response in these instances. And then
So in the better response, you are prescribing which better response to take?
So in the better response, so a player is a job, and the job needs to take the best blocking edge and needs to allocate as much quota as possible to the best edge, and needs to reject the worst edges. So whatever is myopically the best position to the active player of the edge, that's the best response.
All these quotas could be exponentially large numbers. I mean these all these numbers.
Yes.
So it's not,
Yes.
they're not bounded anywhere.
No. And then following determination, we have a potential function. So it took us quite some time to figure out what is monotone in this procedure, but it turns out that the rank of the best proposed edge of the passive player will be somehow monotone, which is not a very straightforward thing, I think, if you see the instance. So just to sum it up, we studied the dynamics of stable allocations. We studied the best response dynamics, always taking the best blocking edge and always reducing all of the worst non-blocking edges, and tackle the best response dynamic, which is just putting in a blocking edge, whatever blocking edge you have. And we showed that in both cases there is a shortest path to stability, but for best response it might be exponential amount. For better response there is an algorithm which I'll show you, which is polynomial alone. And using Markov chains, it's a quite easy argument that both procedures, both best and better response dynamics, actually converge the probability to 1.
So, what's the expected hitting time for the better response dynamics? Because it converges with probability 1, and there exist polynomial length things, but it could be that in expectation it's polynomial or exponential.
If I'm not mistaken, for the hypothesis player, there are also stable matching instances where the expected time is very large, is exponentially large. Okay, I'm not mistaken. Yeah.
Okay.
So we saw the stable matching problem of capacities, this very general extension of it, and myopic procedures that you can stable to this stable solution. Thank you very much.
Yeah, thank you for the talk.
So if we run the Boy proposal algorithm, that would correspond to only picking the unmarried guys and picking their best blocking edges, and that would be converge quickly. So how does that go wrong when you do the more general problem?
So you're saying you start with an empty allocation?
Well, just like if we take the standard Gale-Shapley Boy proposal algorithm, that converges quickly too, right?
Yeah.
So, and that covers, here you were starting with the married guys, well that one's basically only works with the unmarried guys. I'm just wondering why that algorithm then doesn't work for your more general problem. Or if you try to generalize that.
So there is generalization of the Gale-Shapley, which is polynomial at 9. I'm not sure if it's a Gale-Shapley.
I mean, I guess the argument works no matter which matching you start with, right?
Certainly.
So don't assume that you start with the empty matching. I guess.
No.
Oh, maybe that's
Oh,
it.
that was.
Maybe that's it.
Okay.
Yeah.
Thank you.
So maybe I missed something, but when you say polynomial, then what do you mean polynomial in the number of nodes? Or
Yes, number of nodes
so
and encoding size of input. So even if you have a large capacity, only the encoding size of this capacity will be a part of the input, so not the